we say that a region is connected. It's a new vocabulary word. If any 2 points inside that region have a continuous path between them. So like this would be a connected region because for any point A and point B that are inside the region, I can always define some continuous path between those points. Okay. This region over here is not connected because, you know, here's a point A, here's a point B. And if I were to try to draw a path in between those points A and B, then the entire path wouldn't lie inside my region. Or the path wouldn't be continuous. So actually, you don't have to memorize this definition, but as long as you understand what I mean, I think the intuitive sense makes it makes it easier to understand than trying to write down the definition, right? But you get the difference between connected and not connected. You're probably familiar with that word. So we say that a region is simply connected if every closed curve inside the region is homotopic to 0. So let me just give you examples. And the examples are going to make, again, way more sense than the written definition, right? But like, what I mean when I say homotopic to 0 is that, like, if I've got some closed curve C inside this region, homotopic means you can just continuously deform the curve. You know, you can change the shape of the curve, or you can shrink it, or you can expand it. But homotopic to 0 means that I could shrink down the curve continuously down to a little point, right? You can imagine this curve that I just drew. If you just shrink it in all directions, you can just shrink it down to just one little point. That's what it means to be homotopic to 0. Meanwhile, over here in this red region is not simply connected because I can think of a curve, well, specifically a closed curve. I can think of a closed curve that does not shrink down to 0. It doesn't shrink down to a point. Notice that this little closed curve can't shrink down to a point because this part does not belong to the region, you know? So it's not simply connected. Like this one is. In other words, a region is only simply connected if you don't have any holes in it. And since this red region has a hole, then it's not simply connected. So I wrote that a boundary is exactly what you think it is. So like if you have this region R, we would say the interior of the region is all of the set of points that belong to the region but don't belong to the boundary. And then the boundary would be all of the set of points that lie on the very, 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 like, limit of the region, you know? Where, like, I'm not trying to be too mathematical with my definitions, but you get the idea. Like, the boundary would be all the green points. that I just drew. Okay. And so this makes sense, but if I have a simply connected region like this, then the boundary of a simply connected region would be a closed curve. This red region, remember, this red region was not simply connected, and the boundary of this red region is actually two closed curves. There's the outside closed curve, and then there's another closed curve on the inside. But as long as your region is simply connected, then the boundary would just be a closed curve. And I should also say, if I'm being really, really specific and trying to be mathematically accurate, the boundary of a simply connected region, as long as it's two-dimensional, like in the plane, the xy plane, then it would be a closed curve. Or just any 2D surface in space would also, I guess, have a boundary of a, well, I'm trying not to get too wrapped up in the definitions because they're not super important. I think you'll understand what I mean when we have to use it. Good morning. So we talked about what it means to have the curl of a 3D vector field. And, curl of a 3D vector field means this is the nabla operator cross product with the three-dimensional vector field. So that was, the cross product where we took the partial with respect to x and with respect to y and with respect to z. And then let's say that my 3D vector field has components u, v, w. So then that would be the curl after we take the determinant of that 3x3 matrix looking thing. If we want to specifically talk about curl in 2 dimensions, and today we're only going to be dealing with 2-dimensional vector fields, then what does it mean to take the curl of a 2-dimensional vector field? And we can really think of a 2-dimensional vector field as just a vector field where it's kind of like a 3-dimensional vector field, except for the last entry is just going to be 0. Okay? And then these first two entries, u and v, they're only going to be functions of x and y, because I'm talking about a 2-dimensional vector field that lives in like the 2-dimensional plane. And in that case, we could keep the same definition, but this would be u and v and 0. And since u and v are only functions of x and y, anytime I try to take the partial with respect to z, the partial with respect to z is going to be 0, since these u and v functions aren't a function of z. So I can also think about maybe just replacing that with 0. And whenever I take the determinant of this matrix, this is going to be I times 0 minus 0 minus j times 0 minus 0 plus k times the partial of v with respect to x minus the partial of u with respect to y. And so this is always the case whenever we take the curl of a 2-dimensional vector field. And so we can think about the curl of a 2-dimensional vector field as being a scalar. Because we know that every single time we try to treat a 2-dimensional vector field like a 3-dimensional vector field, then the curl is always going to be a vector with 0, 0, and then a third entry. But that third entry is going to be what I'm talking about when I say we treat it as a scalar. And if we try to talk about the curl of a 2D vector field, it's just going to be the partial of v with respect to x minus the partial of u with respect to y, where u is just the first entry in my 2D vector field, and then v is just the second entry of my 2D vector field, right? Okay. So, two theorems that we're going to spend some time on in the next couple weeks. One is called Stokes' theorem and one is called Green's theorem. Stokes' theorem says if you've got a 3D vector field and we have a simply connected two-dimensional surface that lives in 3D space, and the boundary of that 2D surface is a piecewise smooth curve in 3D space, then the path integral of your 3D vector field around the boundary of that 2D surface is equal to the double integral over that 2D surface of the curl of your vector field. Okay? Sounds a little bit crazy, but Green's theorem is a little bit simpler because Green's theorem only applies to two-dimensional vector fields. Green's theorem says exactly the same thing, but if you only think about 2D vector fields that live in the xy plane, and you only think about simply connected regions that live in the 2D plane, in the xy plane. And so notice that these are really saying the same thing. We're taking the path integral over the boundary of a simply connected region of a 2D vector field, and that's going to be equal to the double integral of, what is that? That's just the curl for a two-dimensional vector field. So we say that Green's theorem is a special case of Stokes' theorem. Stokes' theorem more generally applies to, three-dimensional vector fields. But if you think of a two-dimensional vector field as just being a special simplified case of a 3D vector field, then Green's theorem is a special simplified case of Stokes' theorem. Okay, so everybody had enough time to write it down, I assume? Right.
What does piecewise smooth bundle mean?
You missed it because you were late to class.
Oh.
Okay, I'll go over it really fast. So, whenever I say a region is connected, what I mean is that any 2 points within the region, you can have a continuous path between those points where the continuous path lies completely inside the region. So this blue region is connected, the purple region is not connected. Okay? Kind of makes sense. We say a region is simply connected if it doesn't have any holes. So like this green region is simply connected because any closed path could be shrunk down to a point and remain inside the region the whole time. But this red region is not simply connected. We would say the red region is connected, but this red region has a little hole there. And so you can think of a closed curve that lives inside the red region, but you can't shrink it down to a point because of the hole. Okay, so that's the difference between simply connected and connected, but not simply connected. The boundary is the set of points that just lie on the... It's really hard to say this in common language without using the word boundary, right? But it lies on like kind of the edge between the interior of the region and points that are not in the region. And then anytime we're talking about, R is a simply connected region, we're talking about a region that's connected and doesn't have any holes. And then the boundary of the region is just going to be a curve. And as long as your region looks normal, then we call it piecewise smooth. Piecewise smooth, I said this before, but that's like practically everything in real life. Piecewise smooth, you can just think of it as not fractal. Okay? Do you know what I mean by fractal? Let me take a really short tangent. And talk about fractals for a second. So if your region looks like this, where no matter how far you zoom in, the edges are always rough, right? Like it's a fractal pattern, that would not be a piecewise smooth boundary. But in calculus, we never think about fractals or deal with fractals, right? That's a different math class altogether. So as long as your boundary of your region is not a fractal, as long as the boundary of your region is what we would call at least piecewise smooth, then you're good. But yeah, like, again, that's not ideal. It's not piecewise smooth, because that would be that curve that makes the boundary of the Koch snowflake. The curve is continuous, right? There's never any discontinuities, but it's never differentiable. There's no point on there that it's actually differentiable. So, anyways, that doesn't really apply anywhere in our calculus class. So anytime I say the words a piecewise smooth boundary, just think to yourself, oh yeah, that's like practically any boundary. Okay. We're not going to deal with fractal regions. Okay. Really quick, let me try to explain something that you're going to see if you ever look inside your textbook. That is, your textbook will use this notation where they talk about a 2D vector field. And they'll say that the first component of the vector field is m and the second one is n. And whenever your textbook writes this, what do? They say something like m dy plus n dx. It would be a completely valid interpretation whenever you look at this weird thing, because you're like, oh crap, it's got with respect to y and with respect to x, but there's only one integral symbol. A completely valid interpretation when you see that is to just pop in another integral symbol, right? That's fine. It means exactly the same thing. I don't really like this notation. I would prefer, for my own sake, whenever I talk about path integrals, to just write the path integral of f. I think that's neater. I think it sort of means something to me versus what they write. But the way they get there is they say, well, the path integral of f is going to be f dotted with the derivative of your path with respect to whatever parameter you use. Like we might use lowercase t as my parameter. And then we take the integral with respect to t. And then my lower bound would be the lower bound of whatever t is. So like maybe t starts off at a, and at the end of the curve, t is b. Right? So you do something like that. But then we say, well, that dot product is going to be the partial derivative of f. No, sorry. Sorry, I got confused. That's going to be m times, let me be more specific about this curve. So this curve is going to be x of t comma y of t. So my x coordinate and my y coordinate are both functions of t. So then you say that with this dot product, this is going to be m times dx dt plus n times dy dt. And I'm taking this integral or this antiderivative with respect to t. And then they say, well, I could use the antiderivative additivity property to say, well, if my integrand is this term plus that term, I can split this up into two antiderivatives like this. And then they say, well, since these dt's are total differentials, we can cancel them out. That's something you're allowed to do with the dt's. So that's numerator, denominator, they cancel out. And this is numerator, denominator, they cancel out. And then your book can sometimes end up writing this like this, and then they get lazy about notation, and then they delete that. Okay, and so you get this weird like integral, but it's got two different differentials that pop up and they're added together. And I just don't like this. I don't think it's helpful for solving problems, and I don't think it's very intuitive in terms of describing what it's doing or what it means. And so I generally try to avoid that kind of notation, but your book loves it. Like all the homework problems in section 15.4 are like this. So I will try to type up some practice problems using the notation that I like to use, because whenever I go to write your exams, I'm sure I'm going to end up using the notation that I like to use, which is just to write your questions like this instead of with their crazy notation. Because I want you to be able to practice. But if you see this in your textbook, describing like, some integral problem that they want you to do in the homework, just remember that you can always reconstruct it. You can always say, well, what is this trying to say? It's trying to say that m dx dt plus n dy dt. And if that's not enough, remember that this would be f dotted with your curve. And so this is just a path integral, okay? But it means the same thing. I feel like I have to explain the book's notation, and I wish I didn't have to. Another thing about notation is that sometimes you see this. It's an integral symbol with a circle in it. This integral symbol is just trying to indicate to you that the path is closed. That little circle in the middle means that your path is closed. So your book doesn't always use it, and I don't really like to use this symbol a whole lot, but what it means is that, if you've got some path that's going through your plane, call this path gamma. We say it's closed if it starts and it ends in the same spot. So I could either write this as a path integral over gamma, or if I write it like this, it means exactly the same thing, but that little circle just indicates to you that, by the way, you should remember that gamma is a closed path. It's really not important. Not every author uses it, but if you ever see that, it doesn't mean you're doing anything differently. It's just being like, by the way, this path is a closed path. Okay. So let's do a couple examples. Suppose I have this two-dimensional vector field where the first entry is y cubed and the second entry is x cubed plus 3xy squared. And I've got a region like this in my xy plane where this curve on the lower side of my region is the curve y equals x cubed, and the line that makes up the top of my region is y equals x. So remember Green's theorem. Green's theorem says that if I take the path integral over the boundary of R, and I need to say this too about notation. Sorry. Whenever we talk about the boundary of a region, we can use the notation with this stylized Greek lowercase delta. And that's exactly the same symbol we use for the partial derivative. It's also the same symbol we use for the boundary. So I hope that's not too confusing, but that's not partial derivative of R, that's talking about the boundary of the region R. So whenever I write this integral, the curve that I'm integrating this path integral over is the boundary of my region R. And so Green's theorem says that that path integral is equal to the double integral over my region R of the partial of v with respect to x minus the partial of u with respect to y where I would say that in this case, u would be equal to y cubed and v would be equal to x cubed plus 3x y squared. Now, first thing, let's begin by trying to solve this double integral. And then after that, we'll try to solve the path integral, and we'll just see that we get the same answer, right? And we'll try to talk about it afterwards and figure out which one was easier to solve. So for this double integral, we have to take it over the region, and let's think about the integrand first. So the integrand partial of v with respect to x, that would be 3x squared plus 3y squared, and then I've got minus the partial of u with respect to y, which would be minus 3y squared. So it says dA, and I get to choose, do I want to be dx dy or dy dx? And in this case, I don't really think it matters, but maybe it would be easier to define my lower bound on x as, no, my lower bound on y as a function of x. So I'm going to do dy dx, my order of integration. So then the lower bound on my y values is going to be x cubed, and my upper bound on my y values is going to be x. My lower bound on my x values is going to be 0, and my upper bound on my x values is going to be 1. Does everybody see how we set up that double integral? You following so far? Okay. So obviously plus 3y squared minus 3y squared cancels out. And then if I take the antiderivative with respect to y, we'll see what we get. 3x squared is going to become 3x squared y. And for the y, I'm going to plug in x and x cubed. So this is going to be x cubed minus x to the 5th. Yeah. Okay. And then if I plug in, oh no, I have to take the antiderivative first. Here we go, antiderivative. So it'll be 3 times x to the 4th over 4 minus x to the 6th over 6. I plug in 1, and this is 3 times 1/4 minus 1/6. 1/4 minus 1/6 is going to be 3/12 minus 2/12. So it'll be 1/12 times 3, which is 1/4. Okay, so that is what I get for taking the double integral of this region over this region of the curl of this vector field. Okay, that was the right side of Green's theorem. To do the left side of Green's theorem, we're going to take the path integral around the boundary of this region of my vector field. And whenever we talk about the boundary of a region, we're always going to go around it counterclockwise, just like a lot of things in math. Just like when we normally think about angles, we are going to go counterclockwise around this. Does that make sense? So the first thing I would think about is the integral from the origin up to the point 1, 1, where I'm traveling along the path x cubed. Okay? And so that's going to be the integral, well, we'll call this gamma 1. So the bottom part of this is going to be the path gamma 1. And we could say that gamma 1 of t is equal to t comma t cube, right? So my x-coordinate is going to just track with my parameter, and then my y-coordinate would be that parameter cubed. And that way my t variables can be anywhere from 0 up to 1. Okay, that's how I'm going to parameterize the bottom curve. I'll call it gamma 1. And then for the top part, where I'm going back from back from the point 1, 1 to the origin, we'll call this gamma 2. And gamma 2, I have to choose some way to parameterize it as a parametric curve. And what I want is when t is 0, I want x and y to both be 1. So I'm just going to make it 1 minus t, comma, 1 minus t. And that way, whenever t is equal to 1, it'll go back to 0, 0. Okay, so then again, I'll let t take on all the values between 0 and 1. There's a bunch of different ways you could have done that, I think. But that's how I'm going to choose to define these curves, the bottom one, and then the top one. And so to take the curve of the whole boundary of this region, we have to first think about, okay, gamma 1 is going to be my vector field f dotted with d gamma 1 dt, taking the integral with respect to t, and then the lower bound of t is going to be 0 and the upper bound of t is going to be 1. Okay, then I'm not done yet, because to complete the boundary of my region, I have to add to it another integral over gamma 2, where I have my vector field dotted with d gamma 2 dt, and I integrate with respect to t. So let me rewrite this vector field down here, y cube, x cube. X cubed plus 3xy squared. So this first one's going to be integral from 0 to 1 of, I have to think about what would be the derivative of gamma 1 with respect to t. That would be 1 for the first entry. And then 3t squared for the second entry. So if I take the dot product between capital F and d gamma 1 dt, the dot product says multiply these together entry-wise, so like 1 times y cubed. 1 times y cubed is just y cubed. And then I add to that what is the second entries multiplied together. So that would be 3t squared times x cubed plus 3xy squared. 3t squared times x cubed plus 3xy squared. So that's the dot product here. And then I write dt plus, now I have to do the same thing but for my second part of the path integral, going back across the top of the boundary. And that is going to be the integral from 0 to 1 of, again, the dot product is going to be this first entry y cubed times, I have to take the derivative of gamma 2 with respect to t, and that's going to be the vector -1, -1, right? If I take the derivative of this gamma 2 with respect to t, then it'll be -1, -1 for my two entries. So that's easy. So then this is going to have the dot product -y cubed minus x cubed minus 3x squared y, and then dt. For this first integral in black here, I have to replace the x's and the y's using my gamma 1 definitions of x and y in terms of my parameter t. That's pretty important. So I'm going to replace the x's with t and the y's with t cubed, but only for the first integral. So for the first integral, the x's are t's, the y's are t cubed. So whenever I see y cubed, that's going to be t to the 9th. And so then this is going to be t cubed plus 3t to the 7th power. Yeah. And then for the integral across the top, I have to replace, this time, the x's with 1 minus t, and I have to replace the y's with 1 minus t, because that's how I parameterize the top curve. So this is going to be -1 minus t cubed minus 1 minus t cubed minus 3 times 1 minus t cubed dt. So I'm going to simplify as much as I can in this step, and this is going to be t to the 9th plus 9t to the 9th, so that's actually a total of 10t to the 9th, and then plus 3t to the 5th. Okay, the second integral will become -5 integral of 1 minus t to the 3rd power. So for my first integral, I have to use antiderivative power rule, and then when I plug in 0, it's not going to do anything. So I only have to think about antiderivative power rule and then replacing the t's with 1s. And so the first one is going to be t to the 10th power divided by 10 times 10, and then 1 to the 10th power is just 1. Okay. The second term is going to be t to the 6th power divided by 6 times 3, and so it's going to be 1 to the 6th power divided by 2, which is 1/2. Okay, then with this integral, I'm sure there's some of you that could do this in your head, but we could use, let's call it a w substitution. And w is equal to 1 minus t, so that way dw is equal to dt, or negative dw is equal to dt. And then this would be plus 5 integral from 1 to 0 of w to the 3rd power dw. So antiderivative power rule says this is w to the 4th power over 4, So I've got 5 over 4, and then w to the 4th power, when I plug in 0 is nothing, and then minus 1 is just going to be 1. And so what is this going to be? $2.75? My answer is supposed to be 1/4, so that should be negative somehow. I lost track of a negative. And that will be 1/4. Okay, so the Green's theorem, we know it should work in all cases. That's why it's a theorem. But what we just did is we verified that it in fact does work for this particular vector field on this particular region. Okay, so here's my question to you. Was it easier to do this double integral of the curl, or was it easier to do the path integral around the boundary?
Double integral.
The double integral? Yeah. I think in terms of time, too, I think it was a lot faster to do the double integral rather than the whole path integral around the boundary.
The path integral was fun too.
Okay. And, this is the idea. I think this is what the textbook wants you to take away from it, is that Green's theorem can be useful if I give you a problem on an exam where I ask you to calculate a certain path integral. You could translate that problem from being a path integral problem to being just a double integral problem. And then you can solve the double integral more quickly than you could solve the path integral. So if I gave you this, and this is the same exact vector field, but if I give you this vector field, and this time I said, give me the path integral around the circle. So the path integral around the boundary of the region is just the path integral as you trace the unit circle counterclockwise of this vector field. We know from Green's theorem that this is the same as the double integral over the whole region of just the curl, which would be the partial with respect to x of x cubed plus 3xy squared minus the partial with respect to y of y cubed dA. And so let's first just try to do the double integral and see how that turns out. For this double integral, let me simplify it just a little bit first. First step, we say, okay, the partial with respect to x would be x squared plus y squared. And then the partial with respect to y of y cubed would be minus y squared. And I'm missing some 3's. Okay. Yeah. So the plus 3y squared cancels with the minus 3y squared, and this is what we have. I think it would be nice, since this region has radial symmetry, I think it would be nice to convert to polar coordinates. And so in converting to polar coordinates, we know x is equal to r cosine theta. And so I could rewrite this double integral by saying double integral from 0 to 2 pi, from 0 to 1, of 3 times r cosine theta, r dr d theta. Okay.
Square.
Yeah. That's r cos, oh yeah, sorry. X is squared here, so that should be r squared cosine squared theta, r dr d theta. Yeah. Okay. First, integrating with respect to r. Means that we treat theta as a constant. And then the r cube is going to be r to the 4th over 4. and then we plug in r equals 0, and it zeroes everything out. So we plug in r equals 1, and we get 3/4 integral from 0 to 2 pi of cosine squared theta d theta. All right, what trig identity should I use to get rid of the cosine squared and just make it like a nice sine or cosine or something?
1 plus 1 plus 2 theorem.
Yeah. So it's going to be the same thing as 1/2 1 plus cosine 2 theta, right? Right? I think that's it. Okay. So then 1/2 plus cosine 2 theta over 2, or I could just take out the 1/2 and call it 3/8 of all this. That will be theta minus sine of 2 theta divided by 2. So sine of 0 is 0. Sine of 2 pi is 0. So this is just going to be 2 pi, or 3 pi over 4. Okay.
Cos sine of 2 theta.
Huh?
Cos sine of 2 theta.
It is over 2, right?
I'm thinking sine of 4 theta is 0, right? And then sine of 0 is 0, so this term doesn't actually really matter.
The minus, like the sine.
Oh, yeah.
Oh, they're saying when you integrate it, it should have been.
Yeah, the integration of cosine 2 theta is plus sine.
Oh, okay. Yeah, I see what you're saying. Yeah, I took a derivative instead of an antiderivative, right? It should be plus. Yeah. It ends up not mattering, but yeah, you're right. I should have known. Okay, so this should be 3 pi over 4, and having done that, I know that the value of that path integral is also 3 pi over 4, without having to do the path integral. I don't think that the path integral would be nearly as bad this time, because you could do the entire path in one integral, right? You could do this path integral by saying it's 0 to 2 pi of, f dot product with, we'd have to come up with a path, call it gamma. But the way I'm thinking of gamma right now in my head is that it would be cosine t sine t. So as cosine goes from 0 to 2 pi, it's going to go 1 to -1, back to 1, and then the sine is going to help you trace the circle as a parametric curve. So I really don't think that path integral would be nearly as nasty as the previous example we just did. But I think it's still easier to do the double integral, even in this case.
Yeah, cosine 0 4. That would be kind of translate into linear form.
Mm-hmm. So I know we're out of class time, but I want to say this before y'all leave, is that one really bizarre consequence of Green's theorem is that if you think about this two-dimensional vector field, where the first entry is -y over 2, the second entry is x over 2, the curl of this vector field is what? It's the derivative of the second entry with respect to x, which would be 1/2, minus the derivative of the first entry with respect to y, which would be -1/2. So 1/2 minus -1/2 would be 1. So if we tried to use Green's theorem here, and you integrate over some curve this vector field, that would be equal to the double integral over the region enclosed by that curve of the integrand 1 dA. But this, you know that this double integral gives you the area of a region, and so you can actually find the areas of regions by doing path integrals along their boundaries of this particular vector field. And so if I had time, and maybe we'll do this tomorrow, but you can find the formula for the area of an ellipse by coming up with a parametric curve that traces the boundary of the ellipse. And then you use that two-dimensional vector field and you do the path integral over that vector field that actually gives you the area of the ellipse. And so you can come up with some kind of cool area formulas using that. But anyways, maybe tomorrow.